Good afternoon, everyone, and thank you for joining our webinar on maximizing profits with a dedusting system. My name is Greg Boyer, and I am the Marketing Manager for Hosokawa Polymer Systems. Hosokawa Micron Corporation is a global leader in powder processing equipment and systems with headquarters in Osaka, Japan. We have over 1,500 employees worldwide, have production facilities in 5 countries, and 12 technical centers and research facilities. At this point, I'd like to introduce today's presenter, Doug Ort, Division Manager for Hosokawa Polymer Systems.
Thank you very much, Greg. Good afternoon, everyone. Thank you very much for taking time out of your schedules to attend this webinar. My name is Doug Ort, and I'll be your presenter today. I work for Hosokawa Polymer Systems. It's a company located in Berlin, Connecticut. We've been around for over 50 years, providing solutions for recycling over that 50-year history. What we do up there is we design and manufacture equipment, size reduction equipment, granulators, shredders, dedusting separation equipment for post-consumer industrial, plastics, wire and cable. We do a lot of other type applications as well. We get into food, coffee, spices, tea, tobacco, things of that nature. Our business at Hosokawa Polymer Systems is to provide simple solutions for applications that customers have. What I'm going to do in this webinar is go over dedusting and separation. I'm going to cover a little bit of history. I'm going to go into some detail on the different technologies that are out there. I'm going to go into why you may need to dedust, what technologies we have here at Hosokawa Polymer Systems to offer you, and then specifically some applications. I feel it good to go into specific applications while they may or may not apply, because you can see exactly how we apply the technologies. So the history of dedusting and separation. I mean, it can go back thousands of years. It can be as simple as separating heavy metals from iron ore, from streams, things of that nature, taking holes and chaff off of grains. It's been around for a long time. Over the years, these processes have become automated, more sophisticated, just like Hosokawa Polymer Systems has changed our designs and upgraded our equipment over the years as well. Some of the different technologies that exist out there for dedusting and classification or separation. We have mechanical type classifiers with internal classifier wheels or screening decks or vibration decks. And then we have airstream separation, such as elutriation or cascading. In the pictures here, you can see PET bottles with the labels removed. You can see a reinforced PVC membrane with the reinforcement removed. So mechanical separators, here we have 2 types, a screening device and a vibration deck. There are many variations of these, and we'll go into each one. So for screeners, there's linear screeners, circular screeners, cylindrical screeners. Here we have a cylindrical screener. What happens is the feed stream is presented into the feed port, conveyed into the screening device. We have a motor with a gearbox, which is rotating that mesh, whether it's perforated plate or a wire mesh. We have a certain size opening that's going to allow the fine material down out of that unit and the coarse material out the end. So then you get your 2 separate product streams. There are a lot of advantages to this type of unit. It's compact, the cost is low, it's easy to install. There are also drawbacks to this unit. It's very hard to clean. The screen can become plugged very easily. It generates static, so if you have a material such as plastic that can have a static charge, it will add static to the end product. You can't remove things that are not circular as well unless you use a special screen, and then it's dependent upon what you're using. You can't remove angel hair, fiber, shavings. So the efficiency overall is relatively low. You will get some fines out. If you make the screen big enough, you'll get some coarse out the other side. vibration decks. The function of this is to basically vibrate and move the heavy material out the front. It walks out the front with the vibration, and the light fraction will walk out the back. So the advantages are it has a small footprint. It can yield very high capacities, but it's really good for densities of vastly different materials. In this case, we're separating copper from the insulation jacketing for copper wire. We have mechanical air separators. In this case, an airstream with an internal classifier wheel. So the functionality of this type system is we have an airstream carrying material and air up into an internal classifier wheel, which is rotating. We have dueling forces, the force of the air going through the wheel, the force of the wheel spinning. That determines what we call the cut point. So the advantage of this type of system are the capacities can be high, and it yields a very fine cut point. So what does that mean? You can cut down to very fine dust, 40 microns, 10 microns. It's not ideal for removing angel hair or fiber or shavings out of material. It's really used for very fine classification. We also have airstream separators, some type of elutriation system, cascading type air sweep, elutriation system with a mechanical wheel inside. How does an elutriation system work? Well, we're drawing material and air through a blower, pushing it into a vessel. And we have a secondary blower downstream of that, which is also drawing air. So we have air going in and air coming out. The air coming out is larger than the air going in. That can be adjusted. And then you get an additional air into the vessel from the bottom. The overall air of the air coming in, the air coming up from the bottom, sweeps the material, takes the fines out, and discharges it downstream. You can discharge it to a baghouse, to a cyclone, to some other type of device. So the advantages to this type of system are the capacity can be high. It does both dedusting and separation. It's not overly complicated. You can add some anti-static, whether it's through air or deionizing into this system. You can have a relatively quick cut point change by adjusting the airflow. And you can remove dust, fiber, angel hair, things like that out of the coarse material. The drawbacks would be the floor space. It uses a lot of floor space, and there's an airflow balancing act. So when you have your airflow coming in with your original material transport fan, and then you have your airflow being generated downstream by the fine cyclone, or by the fines blower, these, while different airflows, are not independent of one another. So if, for instance, you have a granulator upstream and you're granulating plastics, and all of a sudden you go from feeding it 1,000 pounds an hour to feeding it 2,000 or 3,000 pounds an hour, or vice versa, the load on that first blower is going to vary. Since the load varies, you're going to vary the static pressure, and since the static pressure is proportional to the airflow is going to change. So since that material conveying airflow is changing, the actual dedusting or separation is going to change as well, because that blower has the same setting that it had before. On elutriation or mechanical type, or with a mechanical type, we have another unit, and the functionality has a screw conveyor, which is discharging material into the vessel. It's got an internal wheel which serves two purposes. It generates an airflow, and it also helps disperse the material. So that material then is presented up to the blower on top. The fines are taken off with the airflow, and the coarse drops out the bottom. Some of the drawbacks to this type of device are that there's a lot of mechanical moving parts that wear, that make it hard to clean. There's a lot of static generated in this type of system, and there's varying internal velocities as well, so that the drag force on the particles vary and the cut points not as sharp. It is, however, very good that the efficiency can be high. It can be used both for dedusting and separation, and the footprint is small on this unit. Then we have cascading type, and the functionality of this type is we're metering a feed material into a dedusting system. It has a completely independent airstream. That independent airstream can have deionized air, which will eliminate the static, and then you get the light fraction, which is removed, brought over to a cyclone, and the course drops out the bottom. This type of unit is very good in that it has laminar flow up through the unit. It keeps the same area so that the same drag force is on the material at all times so that you're not varying that. And it's very easy to maintain, very easy to clean, and it does very well for not only dedusting but separation as well. There is a big drawback to this unit, that's ceiling height. Because we're adding a lot of vertical space, we need to make sure that it can fit in where it needs to. We can make modifications to it in some cases to make it fit as well. So why dedust? The people that need to separate labels from PET flake, insulation from copper wire, you know why you need to do that. The people that have a dust problem, maybe you know you have a dust problem, but why do you need to dedust that? Well, all of you have your own reasons. Some of you probably have more reasons than we'll cover here, but these are the majority, the most common reasons that we hear from our customers. In the plastics industry, the biggest reason is that this dust causes problem. It causes off-spec parts. You can have burning in an extruder, an injection molding machine. You can have loss of production. You can have gels on sheet extrusion, blemishes on sheet extrusion. So when that dust doesn't melt at the same rate as a virgin pellet, it causes you quality issues. The downtime for cleaning, you can have this dust collect on the throat of an extruder, melt, and cause bridging on the extruder, and the dies for blow molding, things like that, where you actually have downtime, where you have to go in and physically take things apart, clean them out so that you can continue your production. And some of you have clean room environments, or are making food containers, or are processing food, and your customers just demand that you have to remove the dust. You have to have a cleanly environment, and the material has to be clean. And of course, then that also leads to hazardous airborne dust is never good in a plant, so you want to control that as best possible, and just good old general housekeeping. So we've looked at the different type, or some different type of dedusting and separation systems, and why you may want to dedust. Those of you who separate know why you want to separate. What does Hosokawa Polymer Systems have to offer? So we have a few different models, and throughout all those models, what we like to do is keep a KISS design. And what that means, I didn't know what it meant when I first heard it either. It just means keep it simple, stupid. It means don't overcomplicate things, make it easy to understand, easy to operate, and something that's not going to confuse customers or be too difficult so that they won't utilize it in its best way. So what do we do? How do we KISS our dedusting systems and separation systems? Well, the things that are relatively the same through all our designs is that we have an even air distribution. I'll go into that a little bit later, but that basically means the cut point's going to remain the same, and the drag force on the fines or the angel hair or the dust is always going to be the same. We use static elimination through our systems, and it's used extremely efficiently because we have laminar airflow through our systems. So we have the maximum benefit from static elimination. We have extremely fast cut point adjustment. It's very easy to add more material into the course, to pull more material out with a simple adjustment of a slide gate or an adjustment valve. The maintenance is very low on these units. They very easily can be accessed and cleaned. We can take steps to modify, put in sight windows, put in more access doors, whatever your requirements need. We can make it out of stainless steel, put in wear plates. There's a lot of flexibility. And they're very compact. They use very little floor space because it's vertical. They do use a lot of ceiling height, though. So we have a lot of different models, a lot of different designs. We can dedust or separate from 10 to 10,000 pounds an hour. We could even do more if we needed to. We haven't done more yet to date, but we easily could. We make a lot of custom systems. One of the models that we have is called our DE. This goes back a few years. We still utilize this for some of our customers and some of our applications. It has some benefits. It's very simple. It has some drawbacks as well. Basically, you have a product and airstream going into the deduster, and that is generated from a blower here, and you have a control valve to control the airflow. So you have material handling, bringing it into the deduster, up to the classification zone. The fines and the dust and the air go out the top over to a fine cyclone, and the coarse fraction or heavy fraction is collected and dropped down out of the rotary airlock. So this is very good for fibers. If you have fibers and you put it in some type of cyclonic action, a cyclone or something like that, the material tends to rat nest and form cotton balls. And then that holds on to a lot of the good product, and when it drops down as a coarse product, because it has more mass because it's entrained the good material too, the separation is very inefficient. So because this unit has laminar flow right from the beginning, the fines go right out. They don't tend to rat nest or cling to one another. The one big drawback to this unit is the conveying air is the same as the dedusting air. So you have a very tight range for what's acceptable. If you know what you're doing, if you're always doing the same thing, if the variance in densities between a couple products that you're doing is not great, this type of unit might be for you. If you're doing a real light material that you need to dedust and then a real heavy material, this is not going to be for you because the blower is going to be sized such that you need to transport the material. And it's going to be sized such that you transport the material and dedust it, but since there's such a variance in one material from another, when you go to throttle this valve down, you're going to dampen back your conveying air and you're not going to be able to move material into the system. Another model we have, actually two models, a KS and a KSS. It's our most popular design. It's very easy to use. It's similar to that design I just showed you, with one exception: it has completely independent airflow. So we rely on, in this case, a cyclone with a blower to convey air and material and then meter it through a rotary airlock into the deduster. Or you can have a super sack up here discharging material through a rotary airlock or some other type of valve, or you can have a hopper loader pulling material up and then discharging through the deduster. So the important thing here is we have a completely independent air supply bringing air up through the deduster, which is doing the dedusting, it's doing the deionizing, and removing the fines or the dust, or doing a separation depending upon what you're doing. So let's look at this a little closer. In general, for all of these, the theory is the same. You have a material that you're going to meter into a dedusting system. In this case, we also have a ferrous, non-ferrous metal separator, so we could get out any iron, any brass, any stainless steel. And then that material drops down into the deduster itself. The deduster itself then has a vacuum coming up through it, which is from this fines blower and controlled through the adjustable slide gate, the amount of air that you pull. So then the coarse material drops down through the bottom, and the fine material or angel hair or fiber comes off over here, discharged through the fine cyclone. Examining this even a little bit closer, what's happening inside the deduster? Well, we have fine particles and coarse particles. This represents a coarse particle, the green circle. We have two forces on that. We have a mass force due to the weight or the mass and the gravity, and we have a drag force, which is the updraft of air and the surface area of the material. So when the mass force is greater than the drag force, that part is going to fall down and discharge out the coarse fraction. When you have a fines material or angel hair, then you have a lighter piece of material. You have a smaller mass force. Sure, the drag force is smaller too, but what happens is when you get to a point where the drag force and the mass force are equal, I've used the term cut point, that's what that is exactly. When the mass force and drag force are the same, that's the cut point. And what that means is 50% of the time that material is going to fall in the coarse fraction, and 50% of the time it's going to fall in the fines fraction. So if you need to get a little more material out of the fines into your coarse as good material, you would decrease the airflow and allow, and thus decreasing the drag force and allow that material to drop down. A quick example, if any of you have a loose piece of paper, take it and crumple it up, but not too much, and try to throw it. It doesn't go that far. There's a certain amount of weight on that paper, and then there's air resistance as it moves through the air. If you have a waste paper basket 10 feet away and you crumple it up into a tight ball, you know, you can be shooting like Dr. J if you want to, and that's because the drag force is a lot less, even though the mass of that is the same. Here's just one more example. It's, again, a KS style. The one difference I wanted to show you on this was because we have the airlock as an air brake to keep the evacuation separate from the dedusting, we can go to a negative system. And that just means that none of the materials going through the blower. That has a lot of benefits. The benefit is the blower is not going to wear. The blower is not going to act as a low efficiency pulverizer and generate more dust out of the material. And there's a lot less maintenance involved on that. The MZM is basically the same theory of operation. The difference is it's when you have an extremely high dust or contaminant load that you want to remove. We need a lot more chambers to separate everything, a lot more airflow, and a lot more cascading effect. And then we have some customized systems. I mean, if you have something different, some of our customers have come to us with some really unique applications. From simple applications to complex, we can certainly listen to you and see how what technology we have can fit. Off to the left here, you see an inclined screw. That's screw conveying material before it gets weighed on a Gaylord. And the customer had a problem, even though it was a fractional amount of dust, less than 0.5%, their client didn't want any dust in the material. So we didn't need an airlock because all the material in the screw conveyor was acting as the airlock itself, or air brake. So when we pull our vacuum with our blower downstream through the deduster, we're just getting the airflow up through the deduster. So this worked extremely well. You can see there's deionizing going on the bottom to prevent the static. This material had a huge static charge on it, so that was really important to the customer. And then the fines are collected over here off a fine cyclone. In this case, the blower is enclosed in a sound enclosure. Off to the right is an example that utilizes a bunch of these different technologies. It has our DE type deduster on top because it was a fibrous material. It was PVC roofing. And the primary cut off the granulator released an awful lot amount of the scrim in between the PVC layers. We didn't want those entraining and lowering the efficiency of the PVC collection. Then after further granulation, we have an MZM type classifier to pull off, again, more and more of that fine scrim, polyester scrim they had. And then even after all that, transporting the material a little bit further still released a little bit more of that polyester scrim. So we ran all that material through a cyclone. And as I said before, the cyclone with fiber tends to create cotton balls, and that's exactly what happened. But it was such that it didn't entrain because there was so little left, any of the PVC in it, but it allowed us to use then a linear screener to let the PVC fall down and to have the cotton balls come off the top. So this is a last-ditch effort here to remove any of the last fibers that was in this system. It's been running for over 10 years now, and it's processed probably over 100 million pounds of PVC roofing. I've used the term dedusting and separation. The way we classify dedusting is that we're removing fine particulate out of similar materials. And separation, it's splitting two or more streams of dissimilar materials. So here's the PVC roofing material, could be a sheet up to 10 feet. Here's the 3-4 millimeter final PVC regrind, and here's the polyester scrim. So what are some of the applications for dedusting? Obviously plastics, there's a lot of applications. Injection molding, blow molding is surely one of the biggest users of dedusting type systems. Extrusion and pelletizing, especially master batch with color fillers, is a big use. When you transport material, you certainly can release dust, both virgin pellets and regrind for plastic. Coffees, teas, spices, tobacco, we do a lot of dedusting in those cases as well. So let's look at a couple specific examples. Hopefully they'll be familiar to some of you out there. In this case, it's purgings of plastic that are drooled out of an extruder. The customer not only wanted to recapture this, but wanted to dedust it so that when they used it, they didn't have any processing problems. So what we did is we, one by one, loaded these onto a conveyor. These purge patties are approximately 5 to 10 pounds. We granulated them in a cutting mill. This is a 16 by 26 heavy-duty granulator. It's got 3 fly knives or rotating knives and 2 bed knives, so we're cutting these purgings down to about 5/16 of an inch. That material is dropping out the screen in this granulator into a discharge bin, over to a blower, which is sucking the material out of the granulator and blowing it over to a cyclone. And then out of that cyclone is dropping through a rotary airlock, and it's dropping through our deduster. Again, we have an airflow up through the deduster with deionized air, and you can see here the material dropping out. So here you can see the material dropping out. It's quite a good capacity for this machine. It's probably close to 2,000 pounds an hour. Relatively small regrind. And for those of you dealing with plastics, you can tell this is a plastic bin. So you can see no dust on the side, not even any small 1-2 millimeter particles stuck to the side. And that's because the deionizing in this system has basically eliminated all the static of the regrinds. And it passes the hand test. And the hand test for us is, we put our hand under the deduster, collect the material, look at it, and then just turn our hand over and drop the material out, look at our hand, and see if there's any dust on it. If there's any fine dust in that material, it will stick to your hand 99 times out of 100 anyways. Here's a picture of the regrind, uniform regrind with no dust. And where did the dust go? Well, here's the control for what the cut point is. We're pulling the dust out of the deduster, through the blower, over to a cyclone, into a 55-gallon drum, and then the end product is this. Clean regrind on the left and fine dust on the right. Another example is plastic runners. We had a customer who not only wanted to granulate plastic runners, but wanted us to dedust it to see what the difference was between the granulated plastic and the granulated plastic that's been dedusted. So here we are. This is another granulator. It's a 2-blade rotor, 1 bed knife granulator, very high shear. It's excellent in press side applications, generates very little dust to begin with. And here you go. So here's a plastic bin that we discharge this into. You can certainly see on the hand test, if you want to call it that, some of the dust and the shavings. And again, these shavings, how do you get these out if you're trying to screen them out? They don't screen out because, they're not necessarily presented to a hole that's going to take them out because the holes are small trying to get dust out. And here's a plastic bin with all the material dropping in. And you can see fine dust and even some larger particles, because of the static, are stuck to the side of this. So we ran this through the dedusting system with laminar flow and deionized air. In this case, we did it separately. We put it in a vibratory feeder up top. We discharged that in the rotary airlock and then ran the deduster. And what the yield is clean regrind as well. And here we have a film, plastic liner, and again, no dust on that whatsoever. That material then, as far as the fines, goes over to collect in a 55-gallon drum. And even the transport of the fines 20 feet through a cyclone down into that drum generated static again, and you can see on the sight glass all the plastic and the fines that are collected. So let's get into some separation technology, separation applications. We do a lot for wire and cable recycling, PET flake, removal of labels and fines, auto shredder residue, light fraction taking off, paper recycling, removing of glass, metals, plastics. There are a lot of different applications. This is just a few. Specifically, let's take a look at jewel cases. We have a customer who did about 200,000 pounds an hour of jewel cases. There were no CDs in these cases, just the cases. The cases did, however, all have paper labels inside. They also, some had film covering on the outside. He had, I think, 5 to 6 people, 8 hours a day, removing the paper, and then he would granulate these jewel cases separately to reclaim the plastic. So what we tried to do, or wanted to see if we could accomplish, was to do it in one step. So again, here's the granulator system. I'll look down the bottom for those of you who may not be familiar. We have a 6-inch solid shaft on this 100 horsepower machine. We've got heavy-duty segments, fully welded to this unit, and 3 fly knives, an extremely tight gap on a double angle cut for the knives, and we're cutting all this material into about 5/16 size pieces. It's being discharged out the bottom into a blower, up to a cyclone, down through the deduster. And in this case, we have the deduster turned off, or we have the air completely turned off on the valve. So you can see we're getting everything out the bottom. There's paper, there's plastic, there's a little bit of film, and there's a lot of dust from the paper. So we come over, we make a quick adjustment on the airflow through the deduster, and immediately we're getting good material out, just plastic. Here's a closer look, and a closer look yet. So then all that paper and fine film and dust is going over through the fine cyclone, being collected, and the end result is clean regrind and paper and dust on the other side. One more application is paper recycling, newsprint recycling. Here we're putting bales into a shredder. Shredder is specifically designed for very tight knife gaps, cutter gaps, and it's great for paper, films, and fiber. This customer had a problem with a lot of contaminants in the paper, metals, and other things they wanted to get out. So we shredded that material to approximately 1 to 2 inches. We then ran that material through an MZM type classifier and took out the heavy fraction. In this case, the light fraction went over to a reverse pulse baghouse. And again, with the paper, generates a fair amount of dust. So we want to contain all that. That's why this type of technology is good. It's completely enclosed. It's got filters inside, and we're pulsing those filters clean, so the continual operation is very easy. And this is the heavy fraction. This is all the material that was taken out of that one bale. And what that breaks down into, there's an awful lot of glass in there, an awful lot of metal, and a lot of plastics. And then all these, if they wanted to, could be separated downstream, and they could sell these off. It wasn't much. It was only a percent or two. But when you're doing 5,000 to 10,000 pounds per hour, that equates to a lot of material. And then we talked about the different technologies, some different examples. What causes dust? Let's take a look at that. This is more specific for just the plastics industry. Maybe you're thinking about a deduster. Do I need to invest in a deduster? The answer may be yes, but the answer may also be no. What can you do to minimize dust? So the main things that can cause dust are any type of size reduction, from pelletizing to shredding to granulating. Different types of conveying systems, whether you're conveying regrind or you're pneumatically conveying pellets. The systems have to be designed properly so that you minimize any dust generation, and the overall process conditions for what you're doing. So let's look at size reduction real quick. Again, here's that shredder. You can see the knife gaps are tight, but they're certainly not as tight as you would get in a granulator. So you're going to get some tearing. With that tearing, you're going to generate dust. When you have a granulator, whether it's high speed or low speed, you're also going to generate some dust. There are different types of knife geometries, different types of speed, different types of knife gaps that you can have. The screens in these machines, there's different geometries, there's different percent open areas. There's a lot of variation available for these machines that can minimize or maximize dust depending upon how you look at it. If you have any questions specific to your needs, we'd be happy to answer them after this, or you can email me after the fact. I just wanted to make everyone aware that there's a lot of things to look at while going into how to minimize dust, and these things all need to be looked at. As far as the evacuation, what are things that need to be considered in the design? You know, what's the velocity in the layout? What are the radius, elbows? How far are you conveying? All these type things. If your velocity is too high and you have warm material, you're going to generate a lot of angel hair. If your velocity, discharge velocity into a cyclone or into a vessel is too high, you're going to fracture friable material. So all these things need to be considered when you're designing a material conveying system or size reduction transport system. And then in general, just what's your material? If you have a friable material, a polycarbonate or a nylon, a glass-filled nylon, talc-filled nylon, you know, all that stuff is going to generate more dust than like a TPO type material. What's the temperature that you're processing at? Can you cool that temperature down? The higher temperatures you have, usually the more dust you're going to generate. Here what you see is our deionizing system. Again, we get complete laminar flow up through the unit, so all these positive and negative ions being introduced into that flow do a phenomenal job, very efficient job of neutralizing all the regrind. So taking a look here, I want to go through one specific example. Sort of covers a lot of avenues as to how you can minimize dust. This is a granulator. Anyone who's in the plastics industry and takes a look at this knows this shouldn't be the case. The customer knew it shouldn't be the case, but it was. So what happened here and what can be done? So this was an application where it was blow molding. It's a high HDPE material. It was air conveyed, flash and parts, and a blower cyclone evacuation. I don't know if you can tell from this picture, but up here, this perforated hood, it's been completely wrapped in cellophane and closed off so that all the conveying air for the parts and the flash are going into the granulator. This air is much higher airflow than the discharge air, so that air has to go somewhere. It's blowing out of every crack and crevice in this granulator. Any dust coming out of this granulator is getting blown out, and that's one of the reasons it's so dusty. Also, there's a poor design here. This was a manual bin, and they just converted it by putting a blower on the back, so you're not getting good discharge. On the downstream side, we have a cyclone. It's not a white cyclone, even though it looks white, and there's dust all over it. Mainly, the problem here is that we've got 2 filter bags. It's really not enough filter area to begin with. Becomes clogged quickly, and then it's very hard for this customer to maintain these bags on a daily basis, so they just don't get maintained. They overfill, creates a back pressure, and you're blowing all that dust again. Anywhere you can, anywhere there's a crack, a crevice, it's blowing the air out, it's carrying the dust with it. And again, in this case, the main culprit was just lack of changing the granulator blades. These are extremely chipped, extremely worn. The knife gap was very big. So at the end of the day, what it's doing is acting as a pulverizer, generating a ton more dust than it needed to. So what were the issues in this case? Conveying air, you had an overpressure situation, so you need to balance that airflow, a better designed relief head. Poor discharge out of the granulator, so you need to account for the flowability of the material and the angle of repose to best design something that's going to allow complete discharge out of that unit. Filter area, inadequate filter area off the cyclone collection, so you just need to ensure proper air to cloth or proper filtration on that side. Maintain the filter bags. Let's just make it easier so that the customer doesn't have to do it as often. I'll show you how to do that in a minute. And then damaged knives. Can't stress enough, we're a granulator manufacturer, so this is one thing we know very well. No matter how good our granulator is, someone else's granulator, if the knives are dull, if the knives are chipped, it's going to act as a pulverizer. It's going to generate a lot of dust. So if we take a look at a similar application and what a different customer did, we can see what maybe a proper solution is. In this case, we have a complete perf air relief collection hood. We're conveying the material, tops, tails, bad parts, over to the granulator. They're just dropping by gravity. All the air of conveying is released out of the top here. Material is being granulated. There's a blower on the back side. In this case, that blower has an air bypass, and there's a proper design for all the material to discharge out of the granulator. Here's another example where we're showing proper filter area. So we have 16-inch diameter bags, 2 rows times 3 is 6 bags, more than enough filter area for I think that's 8-inch, so we're looking at about 2,000 CFM through this cyclone. And not only that, the customer didn't really want to maintain these bags at all, so we have a reverse cone, we have through bags, so that all the dust eventually migrates down here. There's a control valve on the bottom. When they want to, they can put a gaylord or whatever they want to underneath this, open this up, get the material, the fine dust out, and keep running. And then lastly, just ensure that you have extremely sharp knives, proper knife gap. Here we show high shear knives, extremely tight knife gap maintained all the way across, and just a good brand new knife and the way a knife should look when it's resharpened. So if you have any applications that you're interested in maybe us testing, we have testing capabilities, or if you have any applications that you want to send to us just to look at, the more information you can give us, the better. Is the application plastics? Is it food? What's the material? The more information you can give us when we talk to you, the better off we'll be. The more intelligently we can come up with a solution and help you improve your process.
Thank you, Doug. We appreciate the presentation, and we will now take some questions. It appears we got a lot of questions throughout the presentation, so we're going to do our best to answer as many as possible. If we're unable to answer your questions live, Doug will contact you offline. All right, first question. Can a dedusting system be retrofitted into an existing granulating system?
Well, the quick answer is yes. A lot of those systems that I showed you early on can be retrofitted. So depending upon which one you need for your system, if you have very round material and you're just looking to get fine dust off and it's round, you could put a screening deck underneath. If you have a cyclone and you have angel hair end fines, you can very easily put a rotary airlock underneath and a dedusting system under that. So basically, all the systems that I showed you, all of them can be retrofitted into existing systems.
Our next question. Please describe static elimination in an elutriating deduster.
Okay, so, there are different ways to eliminate static, and static can wreak havoc in some cases. So the two ways that are primarily used are, one, we can actually introduce water. And some people may say, I don't want water in my product, and in some products you can't do it. But what we do is we introduce water into the granulator, if we're using a granulator, and before the blower to convey the material over to the elutriator, the deduster, whatever type of device you're using. And actually, you can add a lot of water as long as it's in a fine mist into a granulator. That's dependent upon the kilowatt that you're using. You're basically going to evaporate that water into a gas that's going to go out with the airstream. Now, you can run the risk of putting too much water in, not find a mist, and then you're going to get your product wet, but obviously we can help you with that. So what happens is that water neutralizes the static. The other way to do it is by using a deionizer, and what that does is it's a device that generates positive and negative ions, fires then into, in this case, the airstream on a deduster, let's say. you have laminar airflow, so you're not mixing those with anything other than the particles themselves. So that there will neutralize any charged particles immediately. If you put it into a cyclone, they tend to neutralize themselves, and it works, but it's just not as efficient. If you put it into an area like at the discharge of a rotary airlock, again, it can work, but the rotary airlock drops material down. The material is like three-dimensional, it's thick, and you can't get to the material in the middle. So the way that we do it, at the bottom, up through the laminar flow with the deduster, we're cascading all those ions through a single stream of material, and it's just the most efficient way to do it.
Good. Next question. What determines the size of dust that can be removed?
So again, it depends on what type of system you're using. If you're using a screening deck, the hole in the screen would determine that size. If you're using a dedusting or elutriation system, it's the airflow velocity itself.
Okay, next question. Have you ever used this on more abrasive materials for separation of dust only? Also, will you pick up magnets going through this process on abrasive materials?
So yeah, I mean, the answer is yes. It's very easy to make the unit out of an AR plate or with wear plates, and we have done that. So it's very easy to make it for abrasive materials. I'm not exactly sure. I think what is meant by the other part of it is, you know, can you also use metal separation? And yes, there are a lot of different ways to do that. We've actually made our own rare earth cartridges that stick into dedusters, so the material goes through that as well. Or as I showed you, we have ferrous and non-ferrous that can be used before or after the deduster. We can also use magnetic grates that can be used after the deduster.
Okay, next question. Can you separate different materials such as PE from PP?
So the way that the systems work, they're not designed to separate different materials. They're designed to separate different densities. And while I know some materials have different densities, if, for instance, you're granulating a mix of polyethylene and polypropylene through a granulator, let's say, you're going to have approximately the same size for all those materials. So this type of system does not separate different materials, polyethylene, polypropylene, nylons. It separates based on density. There are other types of sorting technologies that can do that.
Okay, next question. What happens if a house bag has a huge area of filtration and so the air to cloth ratio is too low?
So it depends. I mean, basically, if the cyclone is sized right, you're going to be okay. What you want is a cyclone that's sized so that the airflow coming into that with the material is not going to blow out the bottom. If you have the air going out the vortex from the inside of the cyclone, out the top of the cyclone, over to your filters, if you have too high a filter ratio or too high a filter, it just means you're not going to have to clean it as often. The problem lies in when you have too less of a filter, not enough filter area, or it becomes clogged. And then what happens is, you know, you're creating a back pressure. The vortex starts to push material, starts to drop lower, and actually push out the bottom of the cyclone.
Our next question. What can you do with all this dust?
So what can you do with the dust? A lot of people throw the dust away. Some people who have an awful lot of dust, for instance, blow molders, high-density polyethylene, you know, 3,000 to 4,000 pounds an hour, those type people, you know, if you're pulling off 2% dust, that's a fair amount of material. Some people repelletize it in-house. Some people sell it off, but you can do both.
Okay, next question. How much density difference between materials would it make the deduster recommendable for a system.
So what we're looking at is density differences and size differences. So we can have a material that has the same density, i.e. dedusting, and remove the fines from that because we have a much smaller part. When you're trying to remove, for instance, do a separation of different materials, if they're both spheres, let's say, basically you're looking at probably a 1.5 to 1 ratio to be able to remove one from another. So it needs to be relatively large. And in that case, it might be better to go with a separation table of some sort, like a vibratory table.
All right, next question. How long does it take to clean when changing materials or colors?
It depends on the system itself. Again, if it being easy clean needs to be part of the design, it certainly can. All these systems can have smooth surfaces, can have access doors so that you can get in to clean. For instance, the KS deduster on, let's say, a 1,000 pound an hour application, something like that, if you're doing color changes, you can change it usually in less than 10 minutes.
Next question. We'll just make a comment here. Someone had asked if we'll be able to show this presentation after today's time slot. The answer is yes. We are recording this webinar, and we will be posting this webinar to our website by tomorrow. And if you've registered for the webinar, you will receive a notification when the recording is ready, so you can feel free to share it with any colleagues. Next question. Does static elimination really work?
So the answer is yes. Whether you're using moisture or spray mist into it or some type of deionizing, static elimination definitely works. Again, when you're using deionizing, try to keep the ions in a laminar flow to have the maximum capacity, but there is an absolute huge difference when you dedust, when you separate, if you can remove the static charge.
Okay, it looks like we're way over time here, so we're going to just take one more question, and then Doug will respond to any additional questions that are submitted offline. The last question is going to be, can you use one dedusting system for multiple granulators?
You can. I mean, again, the most important thing is to keep the air streams, the conveying stream, separate from the dedusting stream. So we have customers that have a cyclone that's sized properly for 3 inlets. They run 3 granulators into that, and you can have 1 deduster underneath. You can have a dedusting system that has multiple hopper loaders pulling from different locations to dedust. Just need to know all of that going into it and not try to do it after the fact so you don't overtax the cyclone or the conveying system.
Thank you very much, Doug. This concludes our webinar today. If you did submit a question and it did not get answered today, Doug will respond to you offline. If you have any questions regarding any applications, you can definitely use the contact information displayed on the screen. We'd like to thank you for participating in today's webinar, and we encourage you to share the link that you'll receive later today or tomorrow with any friends or colleagues that may benefit. Thank you so much.
Thank you very much.